So I'm supposed to be giving a crash course in Ethernet. This is quite a big topic. Normally, I would do this over a week or two, and I'm trying to cram it into an hour and a half. So things are going to start slow and then kind of get very fast and hectic.
When you say normally, is there some 2-week Jason Manley Ethernet course we can subscribe to?
There was one 2 years ago. So I've, in the interest of trying to save time, I've kind of split this up. There are over 100 slides here, and there's no way we're going to get through all of them. So I've moved 2 of the sections that you may have seen in the outline to my Friday talk, where I'm sort of going to be focusing on how you scale out Ethernet, how you build really big switches out of a lot of little dinky switches, and how we did this in Meerkat specifically. So today's talk is mostly going to focus on sort of the basics of Ethernet. If you've done undergrad comp-sci or electrical engineering and had a course on networks, much of this will be familiar to you. And there's going to be a bit of a focus on multicasting later, because that's sort of a unique capability that this offers. So firstly, what are we trying to do? You've heard over the past few days a lot about these various processing systems. And this talk is focusing on how you interconnect these things, how you build slightly larger ones, and how you route data between these devices. There's also, you can build your correlators and beamformers and things in many different ways. And if you use FPGAs and ASICs, there's a lot of flexibility in the way these things communicate. But mostly, at some point, you have to get the data out of the FPGA and into a conventional computer for further processing. And Ethernet there really shines. And also modern facilities are demanding more and more functionality from these processing systems, and adding things is much easier if you're using industry standards. And then something was mentioned in the last talk that might not be well understood by very many people here, this concept of a corner turn. It's just a giant matrix transpose. When you have very large systems, you can't do this on a single node, so you have to do it between nodes. I'll show a diagram of this in a minute. There are very many different architectures people use to build big correlators and beamformers, so-called FX, XF, and there's various combinations of these things. You can break the problem down in different ways, subbands, time slicing. But they all have this same basic problem where you have to send a subset of data to different nodes for processing. So here's just a simple diagram of an FX correlator. You've got some antennas here on the left. You channelize it, and then you send a subset of those channels to one node, in this case for multiplying and accumulation, and you send a different subset, the same subset from each of these separate F engines, so the same channels to a different node. So there's a transpose operation that needs to happen here. And it turns out this transpose scales with the number of antennas squared. So when you start with really small systems, the problem is trivial and really easy, and often you can do it on one FPGA these days. But once you start getting to hundreds of antennas, the problem becomes really difficult and intractable. So the interesting thing here is you can actually contain this into one block. And to give you a sense of the scale of the problem, there's some pictures here of some other correlators that have been built. This one is the JVLA. You can see some line cards there with lots and lots and lots of wires coming out the back. This one is the Elmer correlator, and there's 16,000 wires here. So it's quite a task to wire up these things without a switched network. If you have a switched network, the n-squared scaling is contained within the switch, and the scaling now is linear into this device. So that's really nice if you can build a big scalable switch. So why do we choose Ethernet? There are lots and lots of packet switch systems out there, and I would counter, why not? It's fast, it's simple, it's cheap, it's really well supported. And the question becomes, well, why haven't we used it before then? And the answer is it's only really recently viable. Ethernet started off very humbly at reasonably slow speeds compared to what we're used to today. But since about 10 gigabits per second, you can build really scientifically valuable instruments at those sorts of speeds. And there's already 400 gigabit Ethernet available now. So what are we looking for in our interconnect? We don't actually typically care about latency. That's a big deal for most Ethernet customers, especially in the financial sector, who really drive Ethernet development because they got lots of money. We don't typically care about virtualization and migration and overlays, which is a big deal in sort of internet environments. We do care about throughput and lossless operation. So, for us, bandwidth matters. We just want to get as many bits down the wires as we can. And we care about scalability, and what I mean here is the number of ports in the system and also the routing table sizes, how the switches, how many routes they can keep track of. And then it's less obvious, perhaps, but it turns out we do actually care about things like robustness, resiliency, reliability, fallback when routes fail and so on in large systems. Because as you add more and more devices into the system, the likelihood of one of them going bad at some point increases. I mentioned that we need to interface to other computers, and Ethernet's the de facto standard for that. Ethernet's also got a very long history, and we hope a long future, so it seems like a good match for radio astronomy. And then there's some other options like InfiniBand, which is often used in scientific environments and high-speed compute environments. And the reason we steer clear of that is because you often need custom PHYs or gearboxes. So there's some custom hardware needed to interface with these things, unless you want to use the old standard, which then isn't really compatible or competitive. And there's some question about long-term multi-vendor support. Ethernet, many vendors make Ethernet parts. And then just to point something out, in many cases for radio astronomy, we only need unidirectional links. You want to send data in one direction down your pipeline. It's very rare that you send it the other way. But Ethernet is inherently bidirectional. And many of the protocols actually rely on reciprocal up-down link speeds. So you can actually cut the link in one way and use Ethernet unidirectionally, but you're going to make a bad time for yourself. And then just another point, Ethernet's gaining in popularity, but there are many correlator designers out there who are still custom designing interconnects, and I'm hoping very few in this room. But okay, what does Ethernet look like? So here's just a generic diagram of an Ethernet network. You've got a bunch of computers here. They connect to a switch or hubs, and these things are all connected by routers, perhaps. And you can kind of scale this thing up by adding more and more of these Lego building blocks together. So I want to talk a little bit about routing or routing types, depending on where you're from. There are kind of four common ones. Unicast is this idea where a sender addresses a bit of data to a single destination node, so it goes from point A to point B. Broadcast is when the sender wants to send that information to everyone. Multicast is when the sender sends out one copy of information and the network then replicates this information and sends it to nodes who have requested a copy of that. Anycast is kind of a unique one and not often come across, but the idea here is that a node will send some data out and the network will decide for you who's going to get it based on a set of predetermined rules. And where this is commonly used is in certain services like DNS. You might have multiple DNS servers, and so you want to look up an address, and any one of those servers can service your request. The network will decide who's going to service the request. So the one that's of interest to us here now is multicast. This sort of gives us a unique opportunity in the radio astronomy world to do commensal observations. Multiple instruments can now run simultaneously and subscribe to the same data stream at your discretion as you want, whichever ones you're interested in. And this can all be done dynamically. Okay, I want to talk a little bit about the open systems interconnect model, which is kind of central to the way Ethernet works. And the idea here is that there's sort of an onion layer approach to sending data around these things. Imagine you've got a sender and a receiver. You want to get some piece of information from that device to this device through some interconnect. It turns out the way these things work is layers are added to that information, to that bit of data or information that you want to send, and they're stripped off again on the receiver to get you back to the original data that you sent. And each one of these layers that's added on performs a specific function. And the idea is that you can swap out these layers without affecting the adjacent ones. So you might want to have a different transport layer, or a different network layer, or a different physical layer. Maybe one guy wants to send it over, a fiber optic, another person wants to send it over a bit of copper. And so you can swap out these layers to pick the protocols that are best suited for your application. So there's 7 layers defined. They're listed there. I'm not going to go through any of them in excruciating detail, but I would like to point out that the function of these layers is different. The lowest level one is the physical layer, and this talks about exchanging raw bits over a physical medium. So that's the physical wires you see in the plugs. That's what's defined in the physical layer. The data link layer tries to do reliable transmission of data frames. So now you've got a concept of frames, chunks of data, between 2 nodes that are connected by this physical layer. Layer 3 tries to structure this and manages a multi-node network, so there are possibly multiple hops now, including addressing and routing and traffic control. Layer 4 tries to make this reliable and includes segmentation, acknowledgement, and multiplexing. So we're going to go through some of these in a little bit more detail. Some nomenclature. We talk about switching or forwarding frames, so layer 2 data, but we route packets at layer 3. This slide's just listing some of the sort of common protocols that you get at each of the layers. And so here I want to point out some of these kind of onion layers that get added on. Here's the data that we want to send, and I've tried to color the data that's being wrapped around this at each time, at each section, each one of these layers. So layer 1 is at the very start. That's the outermost layer. And there's a preamble and a start delimiter to tell the receiver when to start grabbing this. So this is what you see on the wire. And then there's a destination MAC address. We'll talk about source and destination MAC addresses in a little bit. They're optional VLAN tags. So that is layer 2. Then we get to layer 3, these green bits, and there are many more fields here. But here we're talking about IP addresses. And then we get to layer 4. In this case, it's a UDP packet, so it's a very thin wrapper. Then there's the actual data. And at the end of these things, there's a frame check sequence, which the receiver can use to verify that the data was all sent without errors. And there's an interpacket gap, so there's dead time before you can start the next packet. So at the end of this, the next one follows. A little bit about layer 1 versus layer 2 versus layer 3. So in a bust network, and some of you may remember the old 10^2 BNC networks, or if you've used hubs instead of switches, all nodes see all the bits on the wire all the time. In a switch network, switches forwards frames along to relevant recipients based on the destination MAC address, but these switches ignore higher OSI layers. In a routed network, routers forward packets along to the relevant recipients only, but now based on the IP address. MAC address is only relevant to get the packet to the next hop. And you know, we talk about these layers, but it turns out the way modern switches are built, they're all multi-layer devices, and the differences between layer 2 and layer 3 in terms of the ASICs is very blurred. These ASICs make decisions based on arbitrary fields in these frames. And the fancier your ASIC, the deeper into these frames they can see to make these decisions. And for example, here, the Mellanox SN3000, that's the current new range of parts, can look at the first 512 bytes of the packet and make arbitrary decisions as to what it wants to do with that packet based on any of those 512 bytes. So whether you choose to look at the IP address or the MAC address, that's just a programming thing. Here's a table of some of the speeds that Ethernet has gone through. You know, the earliest common one was 10 megabits per second, and that was a single lane. It ran over BNC or the now common RJ45 APAC connector. And that's been pretty much the same up until 1 gigabit per second. And then when 10 gig came along, they tried all sorts of different connectors. And those have all kind of fallen by the wayside. If any of you have played with the Roach 1, you may have seen these CX4 connectors, horrible things that are all wobbly, and if you bump them or breathe on them or so much as look at them, you get bit errors. Now we have SFP plus connectors, but you can also get 10 gig over RJ45. What's interesting here, though, is they changed the signaling standard. So on CX4, there were 4 lanes running at 3 gigs, but now you've got a single lane running at 10. And this has become kind of a running thing here through these later standards. 40 gig now has 4 lanes of 10 gig running in parallel. And the connector is not just a small form factor pluggable, but a quad small form factor pluggable. I'll show you some pictures of these in a minute. And it turns out 40 gigabit per second is already being phased out. So 100 gig is the new standard that's becoming very common, and it's kind of replacing 40 gig. So these earlier standards are still around and still current, even though no one uses 10 megabits per second anymore, but 40 gig is being deprecated in favor of 100 gig. So 100 gig is going to be the next long-lived standard. And 100 gig at the moment is running 4 lanes at 25 gigabits per second to get you your 100 gig. And you can do interesting things with this. You can split this out. You can split it out into 4 25 gig ports or into 2 50 gig ports. And your connector here is either the SFP28, which is backwards compatible with the 10 gig connector, or QSFP28, which is backwards compatible with the 40 gig connector. And 200 gig and 400 gig have also been defined. And here's your first caution and warning. You can split out a 200 gig port into 4 50 gig ports. But if you plug that into one of these, it runs not at 50 gigs. It runs at 25 gigs. Because this uses 1 lane of 50 gig, whereas if you split your 100 gig out, it ran at 225 gigs. So you have to be a little bit careful. Sometimes if you just plug these things in naively, they work, but you don't get the performance you expect. And 200 gig and 400 gig is available now, but it's kind of not standardized, and there's some competing solutions out there, depending on the signaling standard that's being used. So I would hold off on 200 gig or 400 gig deployments at this point, unless you really need that speed. In terms of the PHY options, the sort of connectors and things that get used, we spoke about the base T. These are your RJ45 plugs that go in your laptop. Base CR is also known as direct attached copper. This is a purely passive copper cable. They have these SFP ports on the end. I'll show you some pictures now. There's also base SR, or commonly known as short range. This is multi-mode fiber, and it's commonly over OM3, 4, or 5 multi-mode fiber. And it either uses LC plugs like this, or these new MPO connectors, if there are multiple fibers running in parallel. And here you get runs of about 100 meters to 300 meters. If you want to run longer than that, you go to base LR, and this is long range over single mode fiber, commonly at 1310 nanometers, also using these LC type connectors. And here you get speeds of over, the standards that are running at speeds of over 10 gigabits per second commonly use multiple colors on the fiber to get the high speed. For example, 40 gig base LR4, and your maximum range here is something like 10 kilometers. If you want to run longer than 10 kilometers, you switch to ER or XR, and there are a few different options here, some not so standard. And you get dense wavelength division multiplexing. You can run lots and lots of these channels over a single lane, and you can typically run 80 kilometers and further.
Jason, high density connectors, the MPO.
Yep.
Are there single mode equivalents to that, or it's
you can actually get MPO with single mode fibers in them, and there are some guys who do that to break them out, but it's not very common. There's a 2-kilometer silicon photonics standard that uses that scheme. I think I've got a slide on this towards a bit later. So what do these things look like? Well, you buy a switch. They've all got these sort of cartridge type things, and you slide the transceiver you want in there, or your direct attached copper. So these high-speed switches look a little different to the 1 gig switches you're used to buying at your local, mass mart. But they kind of work the same way. And if you want to plug fiber in there, you get a transceiver. This is a transceiver for multi-mode that takes these MPO connectors. This is a transceiver for the LC type connectors for single mode, longer reach. And you also get these things called Breakout or octopus cables. What this basically does is break out your quad SFP connector into 4 SFP connectors. So you can turn your 40 gig port into 4 10 gig ports, or your 100 gig port into 4 25 gig ports, and I did mention the caution there on the 50 gig links. So you can commonly do this with copper, the CR standard, the so-called direct attached copper, or you can do it with the multi-mode standards, the so-called short range ones, and there's certain other kinds where you can also get away with it, but at this point, you probably want to do a little bit of research. So just a word on some fiber conventions. Multimode fibers, typically 50 or 62 or 128 micrometers. Single mode fiber is a lot smaller. OM3 and OM5 can often be used interchangeably, but there's usually a range penalty on the older standards. And the cost is very similar. So these days, if you're going to put in new multimode fiber, definitely you want to go with OM4, OM4 Plus, or OM5. But there's a color standard to these things that's worth noting. Legacy OM1 and OM2 fiber is typically orange in color. OM3 and OM4 is this sort of aqua color. And then OM4 Plus and OM5, there's a convention now to have that violet. And by the way, this MPO it stands for multi-fiber push-on, but it's got lots of other proprietary names. They're all compatible, though. And then what's interesting is multi-mode fiber is generally more expensive than single-mode fiber, but the transceivers for multi-modes are a lot cheaper than the transceivers for single-mode. So there's kind of a trade-off that you need to make there depending on the length that you want to run and the number of these things you want to deploy. When it comes to single-mode fiber on these higher speed standards, we talk about CWDM or DWDM, and this is wavelength division multiplexing. This is getting multiple lanes running over a single fiber or sets of fibers. And the difference here is in how closely packed these colors are. In coarse wavelength division multiplex, there's 20 nanometer difference between the channels as opposed to 0.8. So these are very densely packed. And the difference typically comes in the lengths that you want to run, what you want to do with this thing. CWDM can occupy wide bands outside of the tuned fiber band. And it's typically used for low-cost point-to-point links up to about 10 kilometers. Meerkat actually uses this as links out to all of our antennas. And if you're careful about losses, you can squeeze out a lot more than 10 kilometers. We run them up to 12, no problem. And there are about 18 of these channels, but they span a very large range of colors on the fiber. In some cases, the colors are fixed. In some cases, you can choose them. If you're running 40 gig base LR4, for example, you have to use these colors to be able to interoperate with other manufacturers' products. And CWDM is often used on fibers centered around 1310 nanometers. That's the center frequency. DWDM, on the other hand, is designed to be muxed onto single fibers and run long distances. There are multiple bands defined on the fiber. We'll talk a little bit about fibers in a moment. But the key thing here is that because they're so closely packed together, they can be amplified by a single sort of dumb amplifier. They don't have to unpack the bits on the wire. It's just an analog amplifier. And then you can run it really long distances. And in the case of coherent systems, that can be thousands of kilometers, between continents and things. And what's really cool about this is you can upgrade the end nodes to more modern technology to get higher speeds while using the existing analog amplifiers along the way. With CWDM, because the bandwidth is so wide on those channels, it's hard to amplify it. So you typically run it point to point without any amplification in the middle. So there are two basic types of single mode fiber. You get G652 and G655, and the difference is in the dispersion of these things. So 652 has zero dispersion around 1310 nanometers. So we're going to use that with CWDM standards, which have their colors around 1310. And G655 has zero or close to zero dispersion around 1510, 1550. So G652 get used for local links. They come in four different versions, A, B, C, and D. They all have zero dispersion at 1310, but A and B have a water peak, so they don't do well with CWDM things where you need a little bit of bandwidth around 1310. They basically tune just for there. C and D are optimized to reduce this water peak, so you can use them. You can get a slightly wider bandwidth over it. And G652D is probably the one to go for. It has superior polarization mode dispersion. So this is the one that's most popular and most commonly used these days. G655 has close to zero dispersion, but not quite zero. And this is the one that's used for longer runs. because it's easy to amplify using these erbidium-doped amplifiers. What do the connectors look like? Well, all SMF is yellow, so it's difficult to figure out if it's 655 or 652. But the connectors on either end are colored depending on how they've been polished. Ultra-physical contact, or UPC, is typically used in data centers where you don't care about losses so much. APC, or angle polished, gets used in timing systems and long-haul links where you really want to minimize reflections. And the UPC connectors are blue, while the APC connectors are green, and you can see a patch lead here on the left that has one on each on either end. And then there's a picture here of one with beige, which we haven't spoken about. And why is this one beige? Trick question. It's not single mode fiber, it's multi-mode fiber. Then there's AOCs, and these things are designed to be drop-in replacements for direct attached copper. So it has a copper electrical interface on either end and fiber coming out the back, but the fiber is welded in. You can't pull it apart like you can with other transceivers. And these things are pretty cheap. You get them in fixed lengths between about 3 meters and 50 meters, so it's the perfect thing to use in your data center. And in my experience, the bit error rate is significantly better with these than copper. Meerkat uses these all over the place. One word of caution, if you buy AOC cables from one vendor, they may not work with another vendor's switches. There are little EPROMs in these SFP and QSFP connectors that identify the cable, and some switches just shut down the port if they detect an untrusted transceiver. But there's usually a sneaky command to disable the check. I want to talk a little bit about silicon photonics. This is kind of a industry upset technology. This is a picture of Mellanox's innards of one of these QSFP connectors. And the idea here is that you can now manufacture these things, so both the lasers and the optical modulation systems, using ordinary silicon manufacturing processes. And it's massively reduced the cost of these things. But assembling them is really tough. The width of these optical channels on the silicon is like 3 meters. Precision work. Intel, though, is shipping 1 million of these 100 gig units a year already, and they're starting 400 gig volume production this year. So it's ramping up quickly, and the costs are plummeting. It used to be that single mode transceivers cost many, many times more than a multi-mode transceiver. Now you can get them for roughly 3 times the price. These prices are from fs.com. And my feeling is that this is eventually going to kill copper. Copper is pretty much reaching end of life. To give you some idea, if you have a passive bit of copper and no amplification, on 10 gig you can run at 7 meters. On 40 gig we could still do 7 meters. On 100 gig now you can run a maximum of 3 meters with a piece of copper, and then the signal integrity plummets. If you use active cables, you can get slightly longer reaches, but there's none available for 100 gig that I could find easily. So based on this, it seems like the future lies in 1550 nanometer SMF, which is what all of these silicon photonics use natively. And this, Lincoln, comes back to your question. These things, there's I forget what they call it, parallel single mode fiber standard now, where you can run up to 2 kilometers with these silicon photonics things. They use those MPO connectors, but with single mode fiber. Okay, so that's sort of layer 1 of the OSI layer. Let's move on to layer 2, Ethernet MAC addresses. So layer 2's function is to handle framing, frame check sequences, interframe gap enforcement, these preambles, and also discarding malformed packets. So they detect if the data all arrived in, if the integrity is intact, and otherwise it drops it. So the layer 2 addresses are called media access control, or MAC addresses, and these can either be universally administered. So this is if you buy a laptop or a NIC, the manufacturer puts a MAC address on there, or they are locally administered addresses, and this is actually what we use for most of the Casper instruments. So if you buy a Roach or a Scarab or something, we assign the MAC addresses, but they are locally administered, so they're not on some central, they weren't assigned to us. There are 2 bits in the MAC address that's interesting. The second last bit of the first octet indicates whether it was a universally administered address or a locally administered address. And the last bit in that octet tells us if it's a unicast or a multicast packet. So a unicast frame is transmitted to all nodes within a collision domain. And in a modern system, a collision domain, because we're typically connecting to switches, is usually just the length of cable between your device and the switch. What happens if a switch doesn't know which port leads to a given MAC address? The answer is it's going to flood the unicast frame to all of its ports. And then your switch becomes a hub. So I'll show some examples of this in a minute. In general, though, only the node with the matching hardware MAC address actually accepts that frame for processing. The others will just ignore it, unless it's in this promiscuous mode, which is generally only used for debugging. The multicast, if that bit is set for multicast, then the idea is that the frame is meant to reach multiple receivers. It will still only be sent once, but NICs will choose to accept it based on their own criteria. And generally, that's a list of accepted multicast MAC addresses. So what's a collision domain? So this is the diagram I showed earlier. If you're connecting to a switch, your collision domain is just your computer and the switch. It's just the cable that's running between you. If you're connecting to a hub, though, or a shared bus, then it's everyone who's on that bus. And why is this significant? Well, if that computer in the top right there wants to send a packet destined for some particular MAC address, it doesn't matter what that MAC address is, the hub is going to send that to everyone. So bandwidth in a collision domain is shared. That's different to in a switching environment. If that computer there wants to send a packet to some destination, the switch will only forward it on to that particular recipient, and none of the other links see that data. How does a switch know which port each MAC address, on which port each MAC address is located? And the answer is it listens on all interfaces all the time. Whenever a packet comes in, the switch checks the header for the sender's MAC address and then records that node's presence on that port in something called a forwarding table, this internal record. The record entry is removed if there are no packets seen from that source after a given timeout. The implication here is that if a node on a network is completely quiet and sends no packets, or if it sends them with malformed packets, the switch will never know where that node is located. So any traffic destined for that node will be flooded out on all ports all the time. So for correct operation on an Ethernet network, all nodes need to send out a packet every once in a while, just so the switches know where it's located. If you're in a radio astronomy environment with FPGAs that's only ever listening on the network, that FPGA does not send a packet out into the network at some point, any data destined for it will be flooded out over the whole network, and your bandwidth on your network will plummet. Let's see an example of how this works. There's our node on the top left trying to send out a packet to that MAC address. The switch doesn't know where that MAC address is, so it floods it out to everyone. But at this point, the switch has learned that that MAC address is located on the port destined for that top left machine. So if the machine on the top right decides it wants to send a packet back to that node, the switch forwards it straight on without flooding it.
I'll point out that in a large system, if you have a bad connection somewhere in the network, you get the same issue.
Yeah. If the packet's malformed, the switch won't make that entry. So if there are bit errors and the frame check sequence didn't check out,
But if
then
the whole thing is set up and then you suddenly develop a link fault.
so if a link goes down, the switch empties this table, and the only way to get that entry back in is to send another packet. Yeah, and the packet the checksum has to check out in most cases, or the entry's not made.
What's the time scale? How often do I have to say I'm here, I'm alive?
So it depends on the vendor of the switch. The fancier ones let you tweak it, you can adjust it. But if you buy a cheap off-the-shelf unmanaged switch, you don't know.
Oh,
Yeah.
okay.
If you send a packet once a second or something like a heartbeat, you're fine. It's usually in the order of tens of seconds to minutes. Question?
When you say when the table empties and the whole bandwidth of the system will go down, for how long?
Indefinitely, until the switch learns where that port is and can send traffic there. So this comes back to this collision domain issue. So it turns your switch into a hub because the switch doesn't know where the destination is. So it will send the data out on all ports. So if anyone is sending any data, that data goes out everywhere. And so if everyone is sending data all the time, then the bandwidth you get is the total bandwidth divided by the number of nodes.
So the speed will build up, like the bandwidth will go up gradually till it gets the full bandwidth, right?
So on a switch, you could, let's take this scenario. Normally, the way Ethernet works with a switch is this node could talk to this node at full line rate. If these were 10 gig links, you could get 10 gigabits per second here. And if this node wants to talk to that node, it could also operate at 10 gigs. So you get 20 gigabits per second. But if the switch doesn't know where these nodes are located, and this guy is sending out 10 gigabits per second, everyone gets that data. Now, those links are already full. So if this node wants to send data to that node, he can't, because this link is already full. Does it make sense? Yes. Okay. Question. What? Sorry.
Quick question. Does this problem happen if two nodes have the same IP address as well?
It depends on if you're on a layer 2 or layer 3 system. So at layer 2, we don't care about IP addresses, we care about MAC addresses, and then it would depend on the ARP table on the sender as to which MAC address was inserted. So it depends on the setup. In general, it's a bad idea to have copies of the same IP address. Don't do that. Okay, and this is just a slide on sort of standard ways of writing MAC addresses, and it can get super awkward because there's a bit reverse notation as well that floats around sometimes, but everyone uses the canonical format, use that. And then just a note here, to broadcast traffic at layer 2, you use the so-called all ones MAC address, so hex FFFFF, and then all nodes in the broadcast domain will receive that. And getting back to our example here, in the same situation we saw now where the node in the top left there wants to send a packet, but now his MAC address reads FFFFF, everyone is going to get it, regardless of what the switch has learnt in its tables or anything. This is an explicit, I want to send this packet to everyone. So that's layer 2. What about at layer 3? Well, layer 3 is responsible for structuring and managing a multi-node network, including addressing, routing, and traffic control. Now you might ask, but what? We already have MAC addresses, so we can already send data to certain nodes, whichever ones we want to, via the layer 2 mechanism. And the answer is layer 3 provides a mechanism to decouple the final destination from the next hop destination. And layer 3 offloads the burden of routing a packet through the network to the network itself, as opposed to the edge nodes. The smarts of how to get a packet from point A to point B live in the network, not on the edges. Can you imagine if all switches on the planet flooded packets out across the entire internet because it didn't know where to find a specific MAC address? It just wouldn't work. So this job is performed by something called a router. And it's their job to figure out how to get data from one point to another point on a hop-by-hop basis. Otherwise, every node in the network would need to know how to, the complete path of the whole network from all nodes to all nodes. So here's the problem scenario. Our green sender over there wants to send something to the red sender here, to the red receiver here on the right, and you can see that in some cases there's an obvious data path, but then it gets to this point and it can either take this route, or it might want to take that route, or it might want to take this route. And how do you know which path that packet should take? And so to try and solve this at layer 2, there are a couple of big problems. Each switch in the network would need to keep a list of all MAC addresses on the network. And if you were to try and do this on the internet scale, there are 48 bits in a MAC address, so that's potentially 256 tera destinations. And it would also have to be able to look these things up very, very quickly. As the packet comes in, it must immediately forward it on again to keep up with decent rates. And it would need to be able to handle this multi-path problem. And there are kind of two protocols that do this. Spanning tree is the old traditional one, and this thing actually blocks all the extra paths. It picks one, and all traffic always goes down the same path. The fancier one is shortest path bridging, where it supports multiple paths, and it will try and balance the traffic across the multiple paths. Unfortunately, very few vendors actually support this, so practically it's useless. So here's our scenario. If we didn't use one of those two protocols, you have this problem of broadcast storms. Don't ever make a network like this with layer 2 switches in between. So here's what happens. Imagine this node on the left now sends a broadcast packet into the network. It arrives at the first switch. That first switch forwards it on out of all the links it should. It hits the next switch there, who then forwards it on as it should. And now it's hit this switch, who's going to forward this on out of all of his links, as he should. So this one has forwarded it back to this one, while this switch has forwarded the packet that came in here onto this guy. And now the switches are all forwarding these packets backwards and forwards, duplicates of each other, indefinitely. They will keep replicating this packet as long as they have power. And all the clients now start seeing these duplicates as well, and you have a right mess. This is known as a broadcast storm. It will consume all the bandwidth on your network. You will not be able to get a packet through anyway. So some switches have a flood control feature that limits the rate of broadcast frames. But the way this is usually solved in industry is with something called spanning tree. So this is designed to add resiliency. So you can connect up your switches with multiple links like this, but it's only going to ever pick one of them. The others get shut off. And so you now have these links there that aren't being used. It's kind of a waste. So this is not great. Also, if that link that you were using fails, it takes a long time for spanning tree to enable the other one. So you get lots of lost data and downtime. Generally, we don't use spanning tree except on the very edges of the network to stop people doing silly things like plugging a cable in from one port to another. In a properly designed, which happens, we've had this. In a properly designed network, you don't really need it. There are various versions of this and extensions and add-ons to deal with improvements and trying to get it faster and working better. But generally, if you want to do this properly, you should use something like shortest path bridging. There's some limitations here as well, but it consolidates all of these functions of the various spanning tree protocols into one. It has limited manufacturer support. In fact, I think I can count on one hand the number of manufacturers supporting this at the moment. Some manufacturers support competing protocols like Trill, so there are other things that try to do similar things, but SPB is the open one. So you might ask, well, why don't we build all of our big switches like this? You know, why don't we build our radio astronomy instruments with SPB? And the way this actually works is it encapsulates the frame you want to send inside another frame for next hop delivery. And this is kind of reinventing the layer 3 wheel. Also, there's a 4096 VLAN limit. It uses a technology called virtual LANs. And there are some extensions for this, but essentially you can get the functionality you want at layer 3 standard and open. Everyone knows about it. Why don't you just use it? Bottom line is layer 2, native layer 2 doesn't scale very well. You need a layer of abstraction to deal with multiple paths of different speeds with potentially different bandwidth loads on the network. So this is where layer 3 comes in, and we're going to talk about that in a little bit, this concept of grouping and subdividing networks. But first, a word on IPv4 versus IPv6. So IPv4, version 4 of the Internet Protocol, is the most widely deployed Internet Protocol and will likely be with us for a long time yet. IPv6 is available, but we're only talking about IPv4. Why is that? Well, IPv4 uses 32-bit addresses. You can address over 4 billion things, while IPv6 uses a 128-bit address, which is apparently enough to address every single grain of sand on the planet. I haven't checked, but that's what they tell me. So we use IPv4 for one simple reason. It uses less memory, less BRAM on the FPGAs, less table space in the switches, which means you can have more devices. And as an example, Mellanox Switch X A6 have can have twice as many IPv4 entries as IPv6, even though the addresses in IPv6 are 4 times larger. Go figure. Okay, so subnets and gateways. How are we doing for time? I'm going to skip over this, actually. Suffice to say that in order to route between subnets, this is a subdivided bit of the network, you have to go through a gateway router. And the idea here is that the transmitter sends a packet addressed to the ultimate destination that it wants to go to, but with a frame addressed to the next hop, the gateway router. I'll show an example of this in a minute. Packets then hop from the router to router until they reach their final destination. Word of caution, some routers check the incoming packets to see if the source network prefix matches its own, so if it comes from the same subnet, and will actually drop the packet and not forward it if there's a mismatch. Cisco, for example, comes configured this way by default. Mellanox does not. So routing is this where the transmitter sends a packet with the IP address to the ultimate destination in a frame addressed to the router, and the router then sends the same packet along with the ultimate IP address destination, but with the MAC address changing to the next router. So here's an example. We want to send a packet from the green node on the left there to the red node on the right, and it's going to send a packet with the MAC address, not of the red machine's MAC address. It's going to use its IP address, but the MAC address is going to be of this layer 3 router. The switch sees this MAC address, knows which port it's on, and forwards it along to the router, who then changes the MAC address to the destination MAC address of that node while keeping the IP address as it was. So that's sort of the concept. So now the routers need to maintain a table of all the IP addresses of the nodes around it. What happens if this green computer wants to send a packet to this red computer who's on a different subnet but connected to the same switch? Now, you might think the sensible thing to do would be for it to send it to this switch, and the switch would forward it on to that machine. It turns out in the default, the way most operating systems and their network stacks work, by default, what would probably happen is this green node would send it up to the router, who would then send it back down to this node. And you can ask questions about that later if you want. Layer 3 has some reserved addresses. Remember, layer 2, the broadcast address was the all ones MAC address. It turns out the all ones host identifier is the broadcast space in layer 3. I'm going to sort of gloss over this in the interest of saving some time. Don't use the first or last address in the subnet is the message here. Layer 4's purpose is to enable connection-oriented communication. It builds in reliability and flow control and multiplexing services on a host. As far as we're concerned for radio astronomy, in general, we only care about the multiplexing part. The connection-oriented reliable comms require overhead and reduce flexibility. Flow control in our case isn't really an option. You can't pause an antenna's data feed. So you just have to deal with it. If there are losses, carry on regardless. There are two basic layer 4 protocols on the Internet Protocol suite, TCP and UDP. TCP is the one that is connection-oriented. It tries to build a reliable link on top of an unreliable transport medium. And it does this by resending packets or asking the transmitter to slow its sending. That's not an option in real-time radio astronomy. So instead, we use the user datagram protocol, UDP. UDP is a best effort service. It's a fire and forget thing. You pump a packet into the network with your appropriate headers on and hope for the best that it arrives at the other end. This makes lots of people very nervous, and I would like to say that it's not a problem if the network is correctly configured. In Meerkat, we have 40 gig network, hundreds of ports. We run all of them losslessly with a 95% aggregate utilization, and we've actually tested them up to 98% line rate, and there are no losses, not a single one over hours and hours. One thing that's nice about UDP, because it's not connection-oriented, you can send to many different nodes. You can round robin between them very efficiently because you don't have to go through a setup and connection setup and teardown process. And it's also naturally lends itself to multicast. Multicast with TCP is a little bit hard. The only basic concept that UDP adds for us is this idea of a source and destination port. And this tells the receiver which socket should process this packet, which socket this packet should go to. And this, in turn, maps to which process on the machine should process this packet. And in this way, you can get multiple services, multiple programs on your computer using the same Ethernet connection. There's 16 bits for these ports, so you can have up to 65,000 different processes sharing the same Ethernet connection. Some of them have been predefined. They used fixed ports for certain services, but a lot of them are available for private use, all those above 49,000. So there's some, if you stick to the rules, which no one ever does, there's just under 20,000 there that you can play around with. For what it's worth, some of the common protocols in Casper, CATCP uses port 7147, Speed uses 7148. Neither are formally assigned. Common protocols. So we don't have much time to go through any of this in any detail. I'm going to give you sort of a hand-wavy overview of a bunch of these things. And the intention of this is to put you on track so that if you want to build yourself an Ethernet network, you know what to Google so that you can figure this out for yourself. You laugh, but there are hundreds of these things, and you look this up and you read it up and you go, well, why should I pick this one over that one? What's the difference? Why? What's common? What is everyone else using? And that's quite a challenge, actually. So I'm going to point out the common ones, the ones you should think about using. And if you're thinking about any other one, please send me an email. Link aggregation. So this is the ability to connect multiple links between two switches and make them look like a single link. So you can double your bandwidth. And you can connect 2, 3, 4, 5, 6, 10, 20 of these things together to get as much bandwidth as you want between two switches. And if you don't feel like setting this up manually, you can turn on a function called Link Aggregation Control Protocol, and you can just plug the cables into your switches, and automatically they will all be combined into one, and you'll get lots more bandwidth. If you've got two network cards on your Linux box, you can even do this between your computer and the switch using something called a Linux bonding driver. The load balancing across the links is hash-based. It's not perfect. We'll talk about this in a little bit, but it does work. You can also do this across multiple chassis. If you've got multiple switches, you can plug cables between them all over the place and turn on link aggregation. If you don't do this, you're going to get broadcast storms like we spoke about before. That's bad. The problem with multi-chassis link aggregation is it's not industry standard. It doesn't interoperate with other vendors. This switch and this switch and this switch and this switch must be the same. They must come from the same manufacturer. They must be running the same operating system. Otherwise, it won't work. LLDP is something you should all think about running. The link layer discovery protocol is very useful. This allows devices to identify all other devices on the subnet. And basically the way this works is everyone periodically sends out an unsolicited packet. It just blasts this into the network, and it says, hey, this is me, this is my host name, this is my IP address, these are my ports, this is what I'm capable of doing. And all the switches actually keep track of this. This is not required for Ethernet to work, but it helps us to map the network. You can then dynamically and automatically generate diagrams to show how things are connected, because everyone else in the network knows what it's plugged into. We actually mandate that everyone needs to run this. And here's an example of something generated by a software package called Observium, which tracks our entire network. And in this case, CBF switch L5, port 26 is connected to port 5 on CBF switch S8. And you can zoom in or zoom out and plot your whole network out this way. ARP, Address Resolution Protocol. Anyone who's worked on the Casper 10 gig, 40 gig, or 100 gig core will hate this. This is the mechanism used to resolve IP addresses to MAC addresses. If you've got a bit of data you want to send to some node, you know it's the node's IP address. How do you know which MAC address to put into the frame? And if you're running an L2 network, this is critical. If it uses the MAC address to figure out where it needs to go. So ARP is basically a little lookup table that keeps track of this, and there's a process running on Casper instruments that populates that table. DHCP is the thing that assigns IP addresses. It's a four-way exchange. Not all Casper hardware supports it, but most now do, so IP addresses can be dynamically assigned. The thing is, this uses a broadcast mechanism. When you turn a node on, it wakes up. It wants to get an IP address. It blasts into the network layer 2 broadcast. I have this MAC address, and this is my host name potentially. Who's got a DHCP lease for me? And how does this work at layer 3? It can't propagate through a router because a router doesn't propagate layer 2 broadcasts. And the answer is you need to run something called a DHCP relay agent on your router if your DHCP server lives on a different subnet. Domain name service is a convenience. This is a thing that resolves a host name to an IP address, and it can give you a few neat benefits. If your service moves to another machine, then this change can be hidden from the clients. You don't have to update your clients to use a different IP address. It can keep the same name. You just update your one DNS server to point to a different machine. Open shortest path first is a layer 3 routing protocol. This is the most common routing protocol in large enterprises. It implements Dijkstra's algorithm, hope I got that right, to find the shortest path between routers. So this is what you run so that the routers can figure out which path your packet should take. It takes into account things like bandwidth, the delay, and the load on each link, and then picks one of them sort of intelligently. And the way this works is each router maintains a network topology map, which allows it to calculate the cost of sending a packet to any particular destination via different routes. And the way this works is all the routers regularly identify to the other adjacent routers all of its costs to its neighboring routers. And this way, the whole network each node can build up a map of the cost to anywhere else in the network relative to itself. OSPF works really well, much better than any of the layer 2 systems, and it can detect topology changes and converge on a new loop-free routing structure within seconds. ECMP, equal cost multipath. This is if you have 2 links and both of them are just as fast, just as heavily loaded, which link are you going to pick to send your packet down? And it turns out it's impossible to do this on a per packet basis. The reason for this is there's rapidly changing latency on different links potentially. Packets could get reordered. Maximum transmission units, the size of packets can differ. And this breaks lots of protocols, most notably TCP used on the internet. RFC 2992 discusses this, and basically the way industry has solved this is they don't load balance per packet, they load balance per flow. And a flow is defined as it's a hash calculation based on a number of header fields. And sometimes you can choose which headers get hashed. But for example, the concept here is if you're sending a packet from one point to another point, it will take a particular path, and it will always take that path. If you're sending from that same node but to a different node, it could potentially take a different path, but it will always take that different path. So for a given flow of traffic, it will always take the same route in both directions. And you can run ECMP at layer 2 or layer 3. Okay, a little bit about multicasting. I've only got a few minutes left here. At layer 2, a specific set of MAC addresses are set aside for multicast. And there's a bit in the MAC address, remember we said earlier, that indicates whether the packet should be unicast or multicast. And there's a specific set of these addresses that have been set aside for multicast. They're listed there. If you are running a pure layer 2 Ethernet stack, multicast traffic will be flooded. So all nodes will see them all the time. If you want multicast to behave like multicast, then you need a layer 2 plus switch. That's what they call it, because it needs to understand IGMP, which is technically a layer 3 signaling mechanism. What is IGMP? It's not to be confused with ICMP, which is the ping. If you ping machines, it's ICMP. IGMP allows nodes to join or leave multicast groups. It's Internet Group Management Protocol. There are 3 versions of this. Version 1 is rarely used these days because it doesn't allow you to leave a group after you've joined it. The only way to leave is to just wait. Version 2 adds the ability for nodes to ask to leave a group, but it only allows for any source multicast. This is in contrast with layer 3, which allows source-specific multicast. So you can join a group, but in version 3, you can additionally say, I only want to receive traffic sent from these guys. In version 2, you can join a group, but you'll get any traffic sent by anyone destined for that group. IGMP versions are backwards compatible, but not forwards. So if you've got a switch that supports version 3, it will also support version 1 and 2. But if you've got a switch that only supports version 1, it won't understand IGMP version 3 signaling. Version 3 requires a lot more complexity in the system. You need to keep a separate table entry for every possible path. So for every source and group combination, rather than just one per group. So any source group. That's the sort of nomenclature. That's the way they write it. Some switches, like the Mellanox devices in Meerkat, only support version 1 and 2 and don't support source-specific multicast. If you send IGMP version 3 packets to it, it does weird things. Switches flood IGMP queries and reports at all ports. Clients can send reports at any time to subscribe or unsubscribe. And you need an IGMP querier somewhere on your network for this to all work properly. So let's look at an example. If you have a pure layer 2 switch, you've got 2 transmitters there and 2 receivers here. It doesn't matter. All of those packets that get multicast out from those 2 transmitters are going to be received by everyone. On a layer 2 plus switch, if those 2 transmitters start sending but no one is subscribed to them, it will drop that traffic. It won't go anywhere. You can actually configure this. There's a little asterisk there, but this is the typical behavior. If, for example, our RX1 node here decides he wants to subscribe to the traffic from TX1, let's say, he's going to send something called an IGMP report. This is going to be flooded out of all ports, and the snooper process, which is running on the switch, is going to see this as well and make an entry into that switch, into the switch's forwarding database, and traffic will then start flowing from the TX1 to the RX1 port. The querier will regularly send out requests for reports. Are you still interested in this group? Do you still want to receive it? If the receiver does not respond within a certain timeout, it will flush that entry from the switch's forwarding database and traffic will stop flowing. That's to be compatible with the version 1 behavior. Multicasting at layer 3 uses the same IGMP signaling mechanism, but now we're not worried about MAC addresses. We use IP addresses, and there's a specific range of IP addresses set aside for this. It's 28 bits in IPv4. But we only have 23 bits of available addressing in the MAC address. So there's a 5-bit overlap here, and the answer is the most significant bits are dropped. That's how that works. So you actually only get 23 bits usable true multicasting if you're on the same side of a router. In layer 2, though, you get no coordination or control of multipath selection for multicasting. You can't control where the multicast tree is routed in layer 2. This is there's new terminology here, and this is maybe a little confusing. I will try and discuss this in a little bit more detail in Friday's talk, where I discuss how this is actually done on Meerkat. Suffice to say, if you're building a small multicast system with 1 switch, layer 2 is great. If you have multiple switches with multiple links to get to those switches, you really want to think about layer 3. Okay, so you've built your Ethernet system. It doesn't work the way you want. How do you debug it? There are 2 common open source tools for this. Wireshark, if you've got a graphics system, or TCP dump if you're remotely connected. Neither are particularly fast. So you drop lots of packets if you're trying to listen to a fast stream. So you only get a sparse sampling of the traffic. Another way to do it is you can capture fast and dump it to disk or RAN disk and dig through it later. And there's some programs like Gulp or Speed2's MC dump. If you're on a switched or routed network, though, you normally only see your subnet's broadcast traffic or unicast traffic destined for you. So if you're debugging on the machine that's receiving the traffic, that's great. But what happens if you're trying to debug FPGA flows? So it's, data's flowing from this FPGA to that FPGA. You're running these tools on your laptop or some other computer. How do you see what traffic is flowing there? And it turns out switches have a nifty feature called port monitor or mirror, where you can make a copy of any of the traffic going into or out of, or both, any port to another port. So that's how you do that. Wireshark looks something like this. It's all nice. You get a list of all the packets that have come in. You can click on them. It unpacks it for you. You can see the raw hex. What about Ethernet on Casper FPGAs? How do we do this practically on an FPGA? If you've ever used the Casper tools, or hopefully you soon will in the tutorials, you drop down something called a yellow block. Yellow blocks are interfaces to hardware things or stuff off of the DSP fabric. And along with that comes a whole bunch of infrastructure that's completely hidden from you that you don't ever need to worry about unless you're building your own Ethernet cores. And the way this basically works is packets come into this core and gets switched either to a microblaze or some Power PC or ARM or some processing system for processing, or they get directed to the DSP fabric for your FPGA code to process. And that decision in Casper is made based on, is the packet UDP? And if it's UDP, is the port equal to my configured fabric port? If both of those things are true, the packet gets unpacked. We remove all the Ethernet and UDP headers and things, so you actually just get the data that you sent. If it's not true, if it's a ping packet or if it's some IGMP report or some obscure thing that we don't understand, the switch, it sends the packet up to the processor to be processed. And this processor runs a whole bunch of stuff. It deals with DHCP, it deals with ARP, it deals with all the typical network protocols that we just discussed. One of those things is the ARP table. It runs around trying to find out all the MAC addresses of all the devices on your subnet and populates this ARP table so that if your DSP fabric ever wants to send a packet to a given IP address, it knows the MAC address already. So you don't have to worry about MAC addresses and IP addresses and things if you're using the Casper stuff. It's all handled for you automatically. This is what the yellow block looks like out of interest. And as I mentioned, Casper Ethernet cores are designed to work with Ethernet, IP, and UDP. Those are the supported protocols at the different layers. And those headers get appended and extracted automatically for you. You just tell it which IP address you want to send to. And you just stream this data into the core, and then when you want to end the packet, you pulse end of frame, and that then will send the packet and be ready to accept another one. How do we interact with switches? This is slightly more obscure. If you run down to your nearest target and buy a 5-port 1 gig unmanaged switch, you don't get this. But if you buy fancy switches, you can actually log into them. Many of them have web interfaces. If you're wanting to do serious work on them, you don't use the web interface to configure it. It's all done through a command line interface that was standardized by Cisco, I think, in about the 80s. And pretty much everyone has copied it, though they'll never admit to it. It's very different, but it's the same. And the commands kind of look something like this. You'll say, if you want to turn off a port, interface Ethernet 1 shutdown. Most of them have this 1/1. And the idea here is if you have a chassis with lots of line cards, this says line card 1, port 1. If you only have one, a 1U switch that only has one ASIC in it, then you put the 1/ in there. There is only one. Another example is show interfaces Ethernet status, and it lists all the ports here, and it tells you if the ports are up or down, the speed they're running at, and anyway, you get the idea. So there's some major limitations to Ethernet. We've sort of worked around them. I'm going to touch on some of these things on Friday because we've pretty much run out of time here. But software-defined networking is an interesting new field that potentially fixes some of the issues that we have and can simplify things enormously. Ethernet's a general purpose thing, and for radio astronomy, we don't need the general purpose. We just need it to do what we want it to do. And SDN is, you can potentially build a system that's centrally managed. So you can have one node or device or server or something on the network tell all the switches how to forward traffic without them trying to figure it out amongst themselves. So this is an area of research. We're sponsoring an MSc project at the moment. I've got a student on this, trying to figure out a better way to do this. Until then, Ethernet works fine. So that's the short and sweet of it. Question?
You spoke of the need for keep-alive packets. Does the Casper firmware do that?
So there's a process that runs around to populate that ARP table. And so it sends out packets basically saying, hey, who's got this IP address? And each one of those that goes out allows the switch to learn its MAC address. And those go out, I think, every 100 milliseconds or so. Is Robin here? Where's Robin? What's the time for our packet?
10 a second.
Yeah, 10 a second.
Go ahead. I'm taking over for Lincoln. It seems to
So
have
you said you can have locally assigned MAC addresses and universal MAC addresses. So do these switches make a distinction between the two?
In general, no. They don't care. it's more a case of if you can't have MAC address collisions on the network. Things will go bad, just like we had a question about IP address collisions. So if it's locally administered, you really want to make sure that everything on your network that is locally administered you know about, and that you don't have the same MAC address in two places. If it's universally administered, you're guaranteed that, because no two addresses will be assigned to different people.
But if the FPGAs are only transmitting, they get 96 MAC.
Yes, you could potentially get away with that. I would need to think that through a little bit, but I think you might be right. Reese?
So in the layer 3, is it the router that changes the MAC address?
Yes.
Okay.
Yeah.
And it does that because it knows the IP address that it needs to?
So the question is it the router that changes the MAC address for the next hop? And the answer is yes. It will enter the MAC address for the next router in the chain, or if it's the last router in the chain, for the destination machine that's supposed to receive it. And it will have a table built up using OSPF and ARP to know which IP addresses surround it and which MAC addresses.
Distinguish between a router and a switch. Is it the same like physical machine that is just configured differently?
Yeah, so that's a good question. Historically, no. They would have been very different machines with very different prices. But these days, the ASICs are so capable that it's the same box, and it's just different software on there. The ASICs have become completely generic. They make their routing decision based on an arbitrary field of data somewhere in the frame. So you can tell them, look at byte offset 32, and if that number is 3, send it here. Or you can tell it, look at byte offset 312, and if the number is 5, send it there. So you can actually have the same bit of kit doing switching or routing or a combination of both. And some of them are doing even fancier things. They can make decisions based on the type of traffic, and they call it deep packet inspection. They can look and see, oh, you're accessing this website. They look at the lower down layers, HTTP traffic, and say, oh, okay, well, we like that website, we're going to make it fast. Or, no, we don't want you accessing that one, we're going to slow it down.
Very controversial.
Yeah. Question?
You mentioned ports and port ranges. I've also noticed that in user ports there's a tendency to, say, assign something at port 50,000, and then the next one is 50,100. And a lot of time, I don't think I've ever seen a time where somebody will assign 50,000, 50,001, 50,000. There's always this gap left. And is that convention, or is there?
Nah, that's just the programmer goes, well, maybe I want to fit something in between these two things at some point, so I'll reserve a little bit of space.
But
there's no reason.
But there's no programmatic reason to reserve space that you could just.
It's just arbitrary.
So sometimes switches come with so-called deep buffers, and they cost like 3 or 4 times the open switch prices. What's the money?
So the question is, switches sometimes come with deep buffers, and I'm going to address this on Friday. I had a whole section on this, but we've run out of time today. That is actually critical. If you have PCs connected to the network, you really do want those deeper buffers, and it's worth paying the money for that. If you're just an FPGA system, you can get by with much cheaper switches. That's actually what we have on Meerkat, that have very shallow buffers, because you can coordinate the FPGA's transmission of packets to sort of skew them. I don't want to get into too much, but look out for Friday's talk.
Yeah, there's actually a comment there. I was amazed. We use these Arista switches in Swarm. We load them up massively with 10 gigabit per second Ethernet. Arista 7050 XX.
Yeah, it's important.
The buffer space, the buffer memory is 9 megabytes.
Yeah, so
It's astounding that you have to.
The crucial thing there is it's global buffer space.
Yeah.
So basically there's a 9 meg buffer, but it's shared amongst all the ports. Any ports can use more or less of that buffer. It's dynamically scaled. Whereas, for example, the Mellanox Switch X systems also have a few megs of buffer, but they're statically assigned to the ports. So each port only gets 100K.
Right.
And that's very easy to overflow.
Yeah. I mean, the key is that that your system has no latency, right? Very little latency.
Well, there's a problem if all the ports are trying to send a packet out on one port. They have to buffer it. You've got to trick it out. So there's a question of
That's probably related. What does it mean when they say it's non-blocking?
So non-blocking means that the bandwidth on any port, on all the ports is equal, and any port can access any other port at full line rate. So if I can just find a picture here of one of these things again. So just ignore the arrows and things, but it comes back to this question that we had earlier. If this is a non-blocking switch, this node might be able to talk to this node at full line rate, and this node could talk to this node at full line rate as well, and they wouldn't interfere with each other.
Okay.
But you might have a switch where internally there's a bottleneck. Let's say all those packets have to pass through a memory or something, and by having these two talking to each other, they're using part of that resource, and now the traffic between these two gets slowed down. I don't know of any guys still, switches of this class who are not making non-blocking switch. They're all non-blocking.
Is that synonymous then with full crossbar?
Yeah, I'm sure there's some obscure difference between them. I don't know what it is, but yes, for our purposes, I believe it's the same thing.
I had we're actually going to take the photo immediately after this session, so we'll end very promptly. But my question was, in that keep alive packet, you said the recipient has to send an occasional packet even if the traffic is unidirectional. Does that apply? You had the green to the red across a very complicated international network. Does it apply in that case?
No, you basically just need to hit the next switch. So
okay,
as long as that guy's sending something to somewhere on his subnet, that switch will know about it.
So L2 occasionally sends a packet back to origin.
Usually these switches and routers are running all sorts of protocols, so even if you're not sending any traffic, if you look at your network port on the side of your machine, you'll see that light blinking every once in a while, even though you're not doing anything. So there are packets bouncing around, LLDP, IGMP, DHCP, someone could be pinging. There's usually something going on, and the timeouts are set long enough that as long as one of those hits at some point, you're okay.
One more from Henry here. Anybody else? Upstairs.
Dan?
Jason, all this extra little stuff that's, monitoring and keeping track of stuff, is it less than 1%? Like, can I run stuff at 99% of my line rate, or is that dangerous?
Yeah, you can. So we've tested our entire network, the whole fabric, and there are multiple layers in this thing, many different switches. And so there's quite a bit of overhead, you would think. We've tested the links. One of our pass criteria was it had to run at 98%. So we allowed for a 2% margin. It turns out we didn't need anywhere near that. I believe you should be able to run it at 99 point something percent, and it will probably work fine.
So it's just a tiny little thing.
Tiny.
It's very sophisticated and complicated, but the actual...
The thing to bear in mind is, these protocols were designed when there were 10 megabit networks, where you wanted to try and, every packet you send costs something, so you don't want to send them unnecessarily. Something like OSPF will send a lot of data and very quickly converge, and then after that it's minutes, between updates, unless something changes. So the overhead becomes less and less, tapers off.
Are the clocks accurate enough that you don't have to worry about differences in clock rates? That could affect how much loss you have.
In these faster systems, so Ethernet used this preamble to sort of lock on, because they're all asynchronous. So if you remember one of these slides here somewhere, there we go. The first bit of bits that are on the wire are this preamble, and that allows the receiver to sort of lock its clock and find the bit edges. Yeah. That's the intention behind that.
But if the receiver and the transmitter have different clock rates,
they do.
It's 10 to the minus 6 or something. It's a crystal.
It just has to stay close enough for the duration of the packet. And then when the next packet comes, there's going to be a new preamble where it can lock onto the bits.
So data are self-clocking.
Yeah, they have their own oscillators, and as Dan says, it's 10 to the E minus. They're very accurate. And the faster, of course, the thing runs, the better the clocks have to be.